So we have learned about probabilistic methods so far. We have learned many methods and then covered chapter 1 to chapter 8 of the textbook. And we will skip the chapter 9, not because it's not interesting. I mean, it contains quite interesting topic, but it's not really about the method that we can use, but more of an interesting topic, which is about quasi-random graphs. And so that's one reason why I feel it must belong to the later topic section better than the part 1. And also some of the stuff in the chapter 9 has been covered in the advanced graph theory course. So I feel that we might skip chapter 9 and then learn some other chapters which is related to certain topic. So I have chosen the chapter 15 of the book, which is about cause, games, and entropy, which is a bit related to the information theory. And I figured that that might be an interesting topic to learn, so I chose to cover this. So I will cover this, and after that I will cover a few more related methods and topics. Then that will probably cover the remaining 6 lectures. So cause and games entropy. So let's start with the cause. So imagine the situation that you are here and you are sending some message to person who is far away. What you want to do is you have a message and you will change your message into strings of binary strings of 0 and 1, and you send them. How you send them is you send using electricity or some other means to send this binary code to the person far away, the recipient. And because the distance is far, and we know that there are many frequencies or noises on the air, so some of the wire transmitting this to, say, while this transmitting this message to the recipient, some of the digit could have been changed to some other long digit because of the noise. But we still want to be able to decode this into the original message. If we have a function between the message and this binary code, binary strings, if this is 1 on 1 and then there is no noise, you just take the inverse of that function, then you can instantly get original message. However, now this digit is changed, so this inverse might give you a totally long message. This is some trouble that we are having, but we want to somehow overcome this. And one simple way is that, of course, if noise is too much, then we cannot overcome it. But if the noise is somewhat small, then we want to, figure out the way to overcome it. And we assume that this noise is somewhat, this noise happens with a somewhat random way. So let's consider the following model. So it's sending some sender is sending some binary string to the recipient, receiver, let's say receiver and sender. Then we assume that each digit can be changed to other digit. So 0 to 1, 1 to 0, with probability, say P. Let's assume that this probability is smaller than half. Then this could be the long digit with some probability, and assume that these events are all mutually independent. Whether this digit is correct and this digit is correct, whether this digit is altered or not, they are all independent events. So this is the situation. One simple way of overcoming this issue is that if this is the original message, we duplicate each digit. Instead of 0, you add 5 0 and 5 0 and 5 1, 5 1, and so on. And if the message is altered at random, then how do you decode it is you take this part and then use the majority rule. There are a number of 0 is bigger, so you write down 0 and 1, 1. Out of 5, either 0 or 1 must occur more number of times, so we write this. Then, before, each digit was received long with probability P. But now this becomes 1, meaning that at least 3 of the digit has to be changed. So 5 choose 3 times P cube plus 5 choose 4 times P4 plus 5 choose 5 times P5 is the probability that it's received wrong. So if P was small, somewhat small, then comparing this P and this number, this is much smaller than P. So by simply doing this, you duplicate each digit into certain number of times. You can actually make sure that the probability of your, getting the wrong message, you can make such probability be as small as possible. However, now the message is so wrong. We also care about efficiency. So in efficiency's point of view, this is not really efficient. We could have communicated very fastly, but now we have to duplicate every digit into certain number of times, which make this sequence long, and which costs time and maybe some money, so it's not so efficient as we want. So what we want is we want the efficient code where the probability that the receiver cannot decode the message is small. So can you find some way that efficiency is not so bad, but the probability of incorrect transmissions are as small as possible? So that's our goal on this code. So let's define a coding scheme. Which consists of a positive integer m and n and a function f, which sends binary string of length m into binary string of length n, which is called the encoding function. So m is typically smaller than n, so you have this code of, say, length 4. So this is the original message, but you duplicate them to get a code of length 20. So this is our function f. And our function g, which sends the binary string of length n into binary string of length m as a decoding function. So in this case, you take the every 5 digit and then take the majority letter. That's your decoding function g. So again, you have this x, which is a binary string of length m, and you encode this as a fx, and you send. And it could add some noise. Then you will receive y, which is again binary string of length n, which is somewhat altered from fx, and you decode it by using g of y, and our transmission is successful if this g of y is same as x. Let's say the rate of transmission as a number which measures the efficiency. So we say the rate of transmission is m divided by n. And let E be something that's representing this noise. Be a random string which is defined by each EI is 1 with probability P and 0 with probability 1 minus P, where the value of EI are all mutually independent. Then this noise can be considered as just adding this E, where addition is modulo 2. So you add 1 and 1, then it becomes 0. You add 0 and 1, it becomes 1. Then this 1 means that that digit is transmitted in a wrong way, and that if this is 0, then that digit is transmitted in a correct way. So let's call the probability of correct transmission as the probability that g of this y, which is f of x plus e, is same of x, where x is chosen uniformly and random from among all length m binary string and independently to this. Let me write it this way. And E is as above, X and E are independent. And plus is vector addition modulo 2. So you identify this string with a vector. So here what's random is X is chosen random and E is chosen random, and both of them are independently chosen. So now, we say that this is a probability of correct transmission. So what we want to find is, we want to find F and G where its rate of transmission is as high as possible, meaning that this is quite efficient, and the probability of correct transmission is as small as possible, meaning that it's quite accurate. So the probability that we get actually we cannot decode the original message is small. So how good can we do? For that, let's define some concept. So let's say H of P be P times log 2P minus 1 minus P times log base 2 minus P, 1 minus P. So this is something called entropy function defined on real number between P between 0 and 1. This is called the entropy function. It has several good properties. So one of them is that n choose Pn is roughly 2 to the h of P plus root of 1 times n. And if you add n choose I with a smaller number, then this is again more or less not much different. So what does this roughly mean? We will learn further about this later when we actually deal with the entropy. But in order to give you some rough idea, let's consider in this way. So, side note. Maybe not side note, okay. It's not directly related to cause, but let me briefly mention what this entropy means. Let's say you have a number between 1 and n, and you need to figure out one number from here. Then you need some information. So let's consider a simple game, Alice and Bob. Alice picks one number from here. Bob is guessing. In order to guess the number, how many questions does Bob has to ask? I mean, Bob is asking a question and Alice is answering with yes or no. Then we easily know that it's, log 2 to the n questions suffice. And at worst case, it is necessary, it is needed. You take a shielding. So in other words, each question, the Bob ask give us 1 bit of information. And then in order to determine the number, you need log 2n bits of information. And in this case, if Bob asks some question, then if, Bob could ask in 2 types, 1 to n, he can divide into 2 sets and then ask whether it's here or here. Then he get 1 bit of information. But if we divide into 3/4 and 1/4, then the information he get might be log 2 over 3 over 4 bits minus, or minus log 2 1/4 bits. So you might be confused about what these numbers are, but we can consider it this way. So 1 to n, there are n choices, and this is 2 to the log 2n. So you take everything in this term, and each question give you 2 possibility, 2 possibility, 2 possibility, 2 possibility, 2 possibility. That has to add up to this much, so that you can ensure that you can actually identify the number. So you can consider this as a 2 to the 1 plus 1 plus 1 plus 1 plus 1 is at least 2 to the log 2n. So you can consider this as an information that's needed to determine one number from here. And each question gives you this much information, and the information you get has to be at least as much as the total information to ensure that you are sure to find the number. But so these are each are the number of bits that you get. So the amount of information that you get. But what if your question is not like divide the set into 2 sets of same one, but in this case, your number that you multiply here in either case is that if you ask this question whether your number belongs to here or here, if the first one is the case, then you actually multiply 3 over 4, which is 2 to the negative log 2 3 over 4. So you get this much bits of information. And the other case, you can get 2 to the negative log 2 1 over 4. So this much bits information, so you can actually multiply 4 here. This is 4. So 2 cases happen, but since we don't know what x is here, so it's quite random whether we can get this case or this case. So in expectation, the number of bits you get is negative. The probability that you get this case is 3 over 4. And the probability that you get this case is 1 over 4. So this is where this formula comes from. So this one, here it's question, but if you get some certain information, you can measure, how many bits does this information carry? You can measure the amount of information. So this is the amount of information of, in discrete world, if you have a probability space, you have information whether your number belongs to this part or this part, where this part has a total probability P and this part has a total probability P. That one information does not actually give the full probability distribution or what happened on the last experiment, but it gives you a partial information, and the amount of that information can be measured by this. That's roughly what this measures. So, with that on side, so let's assume that that's roughly what we understand. So that's the intuition. Then let's figure out how good your coding scheme can be. You have a x, which is a zero-one vector of length m, which has m bits, and you map into fx, which is n bits, and you add e, and you map it back to m bits again. So here, so what do we have here is that if you have a, so if this one is perfect, meaning that for every x and for every e, if we can do this, then there should be a one-to-one map between this and this. So what's this? 0, 1 to the m times all possible spaces of E, which is also n vector. Give me a moment. Of course, this is impossible. So there cannot be a one-to-one map between these two. This one is much bigger. But the E is not just a vector chosen random from here. E is chosen with a, above rule. Where is it? Here, this. And this P is actually smaller than half. So roughly, this carries m bits of information, and this carries n bits of information. And if this were to be possible, the information that E carries, let's say E carries S bits of the information, then we have to have this. Otherwise, the left-hand side carries more information, which is, not really. In that case, this correspondence we have is not possible. So at best scenario is this. And what's this S? As I mentioned here, the average information 1 bit carry when that 1 bit is chosen from 0 and 1 with probability P. It's 1, probability 1 minus P is 0. So this is 1 digit of E. So this S is that there are n digits, and each digit is actually having carried this bits of information. So that's actually HP of n. HP times n. So what I'm saying now is the intuition. We didn't really prove or define what this bits of information. Those are the all intuitive, concept. So best scenario we can hope for is this. So m 1 minus hp of n is probably the optimal thing we can ever hope for. But what Shannon's theorem is saying is near optimal case can be achieved. Let's say epsilon is positive, then there exists a coding scheme with the rate of transmission. So in this case, what's the rate of transmission? You divide both sides by n, then 1 minus hp. So we want it to be big, so it's greater than 1 minus hp minus epsilon. So it cannot be bigger than this. We haven't really proved it, but our intuition tells that because of this reasoning, it cannot be bigger than 1 minus h of p, but it's saying that it's bigger than 1 minus h of p minus epsilon, so this is close to best possible, where the probability of incorrect transmission is less than epsilon. So this is a Shannon theorem. So, but we can actually show that this number is best possible. So the previous one was kind of intuition, but we can actually, show that if we want to make sure the probability of incorrect transmission is small, then this is almost best we can hope for. So how we can actually show it is that you have x and fx, and fx plus e, and g of fx plus e. So here we actually measured how many bits of information it carries, but alternatively what we can do, it's almost equivalent, but alternatively what we can say is that with high probability, E has 1 plus zero of 1 times np digits 1. So this y is with high probability. Y is of having distance 1 plus zero of 1 np from fx. But there are 2 to the m input world, right? So if you consider fx, there are 2 to the m many, and each one of them has a typical, for each one of them we consider the having ball of distance at most this, and at most this, at most this, at most this, at most this, at most this. Then each of the one ball contains n choose pn element. So there are totally, so let's say this is a typical output. Typical output all has that many digits 1. Then the number of typical output here is, for here this many, for here again this many. So there are 2 to the m, n times p, n choose pn, which is, if you compute it, this many. which is, let's assume that m is bigger than 1 minus hp plus epsilon to get the contradiction. If we have that assumption, then this is actually quite bigger than 2 to the n plus some small number times n, where this depending on epsilon. That means there are quite an overlap here, which are, between this input. And as long as we have a case that the E, so your X is here, but E sends to, one of here, or here E sends to here, and E sends to here. So your fx plus E ends up in this overlap. Then, give me a moment. So this is, I said this is a proof, but this is also not proof for the intuition. Give me a moment. Maybe we shouldn't spend too much time on here. So this, also give you an intuition that, let's say, I'm not going to claim this as a proof, but let's say this also give you the intuition that why this Shannon theorem is best possible. So in next video, we will define what's called group code, and then we will actually prove this Shannon theorem.